So reminder, tomorrow's your work day. Second one this week, really. 2 big items due tomorrow and Tuesday. So no excuses. Make sure you get both done. Homework check at the end of class tomorrow. So come with your laptops, your chargers. I don't have extras. And so you can get things done. Of course, work on homeworks, watch videos, ask for help. I'm happy to help. And then if you have nothing else for me to do, of course, I don't mind you working on another class, okay? I'm going to treat you like the young adults that you are. I'm not going to harass you. I'm going to check to see if you did your quiz. I'm going to check to see if you did this. If you say you did, then you did. But just be responsible. Oh, thanks, Ed. Be responsible. Make sure you get everything done. Use the time. I mean, your AP Pre-Calc teacher gives you lots of time in class to get things done. And so use it. And use me. Take advantage of me. All right. So we are going to finish up with 2.10 today. More about inverses of exponential functions. I think you guys did a great job yesterday, as I told you. I think you'll think this is just as easy. A lot of review. All right, and pretty short notes, short homework, okay? So let's get started by reminding ourselves, when you hear the word inverse, I want your brains to immediately say to you, switch x and y. Like the most basic concept of an inverse is switch x and y. That's a really, really important thing. It works in your table of values, the points on a graph, domain and range, and x equals something, asymptote becomes a y equals something, asymptote, switch x and y in an inverse. And you'll see that again in the last thing I have to show you today, so keep that in mind. And we also learned yesterday that exponential functions have an inverse, that is logs, right? Logs and exponential functions are inverses of each other. So we talk about them a lot hand in hand, okay? Some reminders. When you don't see a base on the word log, what base is it? 10, right? We call it a common log. We know if it's not there, it's a 10. Got to know that, okay? How about if you don't see a base on an ln log? That is what? E, not 10, right? Okay? Whenever the word log comes out of my mouth, you read something about a log, you hear anything about log, includes natural logs, okay? Natural logs are a type of log. They're all one family. In fact, you could even say log base e of x. That is the same as natural log x. They are the same thing. Somebody, somewhere, at some time, for some reason, I don't know the answer to any of those, said, let's give this guy his own special name because it has a base that's a letter instead of numbers. That's pretty much the only difference, okay? It's still a log. So as we go through all the different transformations for the zillionth time to our parent function of a log, when I say log, I include natural logs, okay? So let's start by talking about the parent function of a log, most basic graph, log base b of x. That's your parent function, okay, or a natural log. Then we have all the transformations. Those are your movements that move your graph, change the shape of it, all of that stuff, okay? And all of this that I'm going to tell you is a review of stuff we've done before. So a vertical dilation represents itself as an A right after the equal sign multiplied by the log and the equation. You've seen it in every other graph. A stretches or shrinks the graph vertically. You can still say stretch or shrink. That's still valid, but dilation is better. Plus, it's one word. Instead of having to remember which one is stretch, which one is shrink, dilation covers both and is perfectly fine. And something to keep in mind, you will have no negatives, no negative A, or I shouldn't say that, no negative dilations. Let's say that. And I'll bring back I'll talk about that more in a second, okay? But I kept getting that question today, so I wanted to just write it there. Okay, notice there's nothing here that says horizontal dilation. We've had horizontal dilations with other parent functions, exponentials, quadratics, things like that. But let me just remind you, that's when there's a number inside the parentheses, and we would say that's a horizontal dilation by a factor of 1/2. That's when you have to flip it, okay? These are just straightforward. Whatever it is, you just do, okay? We have flips in the x and the y-axis, and that is all dependent on where the negative is. Now, there's a word that I hate in this class, and I very, very rarely use it, and that word is memorize. Memorizing something is really good short term, okay? Think about I don't know why, I shouldn't say it, but I don't know why some teachers make you guys like memorize all the capitals of the states. I mean, maybe there's a reason, or the presidents in order or whatever. That's great. That's note card, memorize. You cram for it right before the test, and you spit out that information because it's right in the front of your brain. But you guys have a lot going on in your brain, right? You have 7 classes. I can speak for myself, so I can probably speak for your other teachers. You're getting something new thrown at you every single day. And that's just in your school day. So that doesn't even count your family life, the world around you outside of school. So, how do you remember every few months this comes up, and how do you remember it? And so, I'm giving you a little bit of a speech about being a good student right now, because it's very, very helpful in this class. And that is this. So, you see this every few months, and you're like, oh, yeah, I can never remember. Is this a flip over the x-axis, or is this a flip over the y-axis? And same thing with this one. Come up with a backup plan. There are a lot of things that you don't memorize that you know that can help you figure this out. For example, if you were like really struggling with this, you could come up with, let me do this. Think about, and I'm just going to share with you one of these little situations that I think about. This is a quadratic, right? We are really familiar, we should be anyway, with quadratics, right? X to the second power. If it's a positive A in front, I always say positive people smile. You guys know the end behavior, up, up. X squared is happy, smiling parabola. The minute you see a negative in front of it, it flips, right? What did it flip over? It flips over the x-axis. So I could put a negative in front of any parent function, and I already know now, because I know this graph, that it flips over the x-axis. Use things like that to help you. It's in there somewhere. Find a way to find it. And then this is the other one, right? This is the other one. There's only 2. So if you know one of them, you know that's the other one, okay? Translations are also called shifts. You can use either word, left, right, up, and down. And that comes from H and K. Right? H and K. We know that H is your left and right movement. You can maybe think of it as horizontal. And don't forget, it's opposite. Minus H is to the right, plus H is to the left. And we can always find H because it'll be in the parentheses. And then K is your up and down, but it's not opposite. How many times have you heard those words from me, from other math teachers? Nothing has changed. The only thing that changes is the starting points, the parent function. Okay? So put it all together. It basically breaks down to A, H, and K again. So Algebra 2, the class right before this, to this class. One of the big differences is, which I don't like about Algebra 2, and I like about this class, is in Algebra 2, we're very, very graph focused. If you think back, if you can remember back to your Algebra 2 world, there was a lot of focus on making nice, perfect, pretty graphs with very good points, showing all of these features on the graph and being graded on the actual graph. In this class, we don't worry so much about the physical making of a graph. In this class, it's about being able to, first of all, use your graphing calculator to graph, okay, and manipulate the screen to find what you're looking for and use your calc features like intersect and min, max, all that. Another thing that you have to do is be able to tell or describe what the transformations are by looking at it written in algebraic form. And that's what we're going to do right here. We're going to say in words, what does that 3 do to the parent function? And another big thing that we do in this class is, of course, and we're going to do one of these in a second, review of yesterday's, we know how to sketch a graph. We can find some key points and make the general shape of it. But really, this is where the money is being able to describe all the key features of the graph. And we keep doing that, okay? So let's go back to this. And we've done this before with other types of parent functions, okay? So they're giving us 2 parent functions here. Those are parent functions. They just gave f of x, they're calling this the log, natural log parent function, and g of x is logs. Really no big deal, just one's log, one's natural log. And then we're going to describe in words what transformations are being done to the parent function, and we're going to write the XY rule. Yeah. Why am I doing that? Why is it like that? Yes, thank you. Sorry about that. Really? All right, I'm back. Thanks. Let me know if I do that again. Sorry, Red. Okay, so h of x. Take a look at it. This is interpreting a language. Some of you might speak other languages besides English. Yay for you. I'm jealous. But think about this. When you look at all these math numbers, of course, and all the symbols, and the placement of where they are and things like that, that's interpreting what is happening just by looking at this. Not everybody can do that. What is this 3 going to do to log x? What kind of transformation is that? Yeah. Up 3, right? How do we know? Wait, so this is important. What tells you that that's up 3? Because your teacher just told you that number that comes after the equal sign is a vertical dilation. How do we know? And it sounded, I think at least one person said that said it right. I didn't hear any wrong answers. But what makes this up 3? What were you able to tell, Riley? Yeah, just that little plus symbol, that little innocent plus symbol, where it is in relation to the 3 in the log, you know that that's really your k value, right? You don't have to rewrite it in this form, but that's what we would normally think of it as. Okay, so that's important. So let's describe in words what is happening. H of x, so that's this graph, is the graph of its parent function g of x. And that would be a shift or a translated or shifted up 3 units, right? Somehow putting the correct words in there in some order. There's more than one way of writing that, but that's it. That's the only transformation. You take all your parent function points. Let's call them xy. We're about to do our xy rule. This is your parent function, a whole bunch of points, right? A graph is made up of a whole bunch of these. And what did we do to it to get this graph? So what you have to do is ask yourself, what does this 3 affect? Does it affect the x or does it affect the y? Well, if you go up or down, that's going to affect the y. So if you go up on the graph, you would be adding 3 to all your y values. That's your new rule. Okay? Good? Problem B has a whole bunch of stuff going on. It has 3 of them. There's a negative, there's a 2, there's a negative 3 or minus 3. Let's just take a look at what each of these does. Let's actually just jump right into it. Let's just jump right into writing it and save ourselves some time. So f of x, this graph, is the graph of, unfortunately, Jean, the lady that makes these, used f of x twice. Let's just make this a capital F to differentiate them, okay? So this little f of x is the graph of the parent function, f of x. Why did I use that one? Because it has ln in it. No big deal. Okay, now let's list in any order what happened. This negative right after the equal sign, we know it's a reflection, but we have to say which one. Think about your parabola. That's a reflection or flip over the x-axis. Okay, there's one. Then we have the 2. Notice it's right up against the log, so that's like our vertical dilation. Over the x-axis, a vertical dilation by factor of what? What am I going to put here? By factor of what? No, we don't flip those. What I'm getting at is we don't include the negative, right? It's a factor of 2. When do we do the flipping? It's only when it's the horizontal ones, okay? And we're not doing this. So remember, if it's inside the parentheses, weird stuff happens. On the outside, it's very straightforward, okay? So what I'm getting at here is it's a factor of 2 because dilations are never negative. That's what I was saying up in the notes above. Okay, by factor of 2, not negative 2, that would be wrong. And we would go which direction with this minus 3? Right, because it's in parentheses and it's opposite. And shift 3 units right. So it's not enough just to say shift or translate. You want to say which direction and how many units. Okay? In any order, that would be fine. Now let's talk about the XY rule. Here's my parent function, right? Whole bunch of ordered pairs. What are those 3 transformations going to do to that point? Well, it's important, just like on the first one we did, to identify which letter these things do affect, okay? And then I'm going to show you a trick, which I've already shown you, but I want to, tricks are great, but they're really only great in the moment unless you use them every day, because then you're not going to really remember. So I always like to show you how to find it with what you have, and then I can show you a little shortcut, like I did with the finding log, not log-based something. So you have more than one way of getting your answer. So let's just take it one by one. This negative, we know it's a reflection over the x-axis. Fine. What does that do to the point? Does it affect the x or the y? And if I was out there walking around helping you guys and you're like, oh, which one does it affect? If you just ask me, that's one of those that doesn't roll off the top of my head. But I know how I can figure it out without guessing or going and looking at my key, okay? And that's this. Think about it in your head or write it. If I have a point in quadrant 1, let me call her 2, 3. That's that point, okay? And I reflect it over the x-axis. It's now here. What is my new point? It's still positive 2, right? But the 3 becomes negative. So just by coming up with something I already know, I can answer this question. It's not memorization, okay? So I can think about that, draw myself a quick little graph, and come up with the right answer. So we just discovered that the negative is going to affect the y value. Also the 2, let's just get that out of the way. The 2 is the word vertical is in it, vertical dilation. Vertical is up or down, that affects the y values. And of course, going right 3, left or right, that's going to change my x value, right? If I'm at 2, 3, and I go right 3, I'm going to add 3 to the 2. I'll be at 5, 3. Okay, but remember something I told you when we did this before? If you say no, you're proving my point, which is perfectly fine. I told you something about this, how you could know super quick which one it affects, but it was in the moment, right? So you probably don't remember. So that's why I want you to have other ways of finding things. But here's what I was going to say. If you are a symbol or a number, a negative or a number in the parentheses, it's always going to affect the x-axis. If you're on the outside of the parentheses, it's always going to affect the y value. We just saw it. This number is on the outside of the parentheses. It affected the y value. This negative 2 is on the outside, affects the y value. Here's a number inside, it affects the x value. It's going to work like that every single time. So you don't really have to go through that whole process, but you can do it if you had to. Okay? Does that make sense? Thanks, Emily. Okay, so when I take my points right 3, right, I move my point right 3, mathematically, what does that do to the x value? It adds 3, right? Don't get caught in a trap of, oh, I see minus 3, so I'm just going to write minus 3. Think about what you're doing, right? Okay, that's all that's happening to the x value. The y value, to flip, you change the sign of the y value. So I'm going to put a negative. Negative, multiplying something by a negative changes its sign. And you would multiply all the y values by 2 to stretch it or dilate it by a factor of 2. So that's your new rule. Okay? Last one of these. You might notice that this one looks a little funny. It is. It's not written in the traditional x minus h form. So we want to put it in that form. Whether you do it in your head or you write it out is up to you. I'm a write it out kind of girl, and I'm going to show you what I mean. So first I want to put the x first, all right? X is negative the way it's given to us, and 2 is positive. So all I did is switch their places. I didn't do anything. And I want x to be positive. It's not going to change the fact that this is going to flip over the y-axis, but let me show you. When I factor the negative out, what's left is x minus 2. Okay? You have to do that to really see the proper flip over the y-axis right to transformations. Now, typically you'll see brackets around all of that, and then of course. So brackets are just the second level of parentheses. Would you see double parentheses? Sure. It's not a hard and fast rule. You could write either one. You would see either one. Either way, you should see that all of that is in parentheses. All of that will affect the x value. But you could also, go through all those little tests and stuff that I just talked about. Okay, so this is right to reflection over the other one. The other. We know this one. We know this one is flipping over the x-axis. This is the other one, so it must be the y-axis. Okay, so y is the graph of the parent function, which is g of x. And name those two in any order you want. Shifted right to units and reflected or flipped over the y-axis. Okay. Every year I say I'm going to improve my handwriting, and I just don't. So I apologize. I should write a little nicer. That's why I should never be an English teacher. Okay, so like we just said, everything is happening to the x values. Nothing's happening to the y values. Okay? So what's happening to my x values? I'm going to have to put a negative in front. That's going to change the sign or flip it over the y-axis. And right to, again, mathematically would be plus 2. And there's nothing on the outside. We didn't go up, down. We didn't stretch or shrink. We didn't flip over the x-axis, so nothing happens to the y value. Okay? Good on those? Okay. Review from yesterday, one of the graphs. So next page, example 8a, we're going to do. I'm just making sure you guys have time to finish writing this. Okay, so let me just give you a heads up what we're doing. We'll do this problem real quick, review of what we did yesterday. So if you understood yesterday, fine. If you weren't here yesterday, here you go. Here's the lesson. And then the homework is really short, like I said, 1 through 6 and 10 through 12. 10 through 12 are super, 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 super important and super, super, super easy. But there's none in the notes for me to teach you. So when we're done with this one, we're going to do 10 through 12 together. Me still teaching, but also getting your homework done at the same time. Okay, so just giving you a heads up. All right, so example 8, we're going to describe how what the transformation is, and then graph it using our graphing calculator and answer some questions. Really important stuff, okay? So just first of all, my parent function is natural log x. That plus 2 in parentheses, what direction does that move us? Left to. So we don't have to write shifts left to. You guys get the point. If you have to describe it, or it'd be a multiple choice question probably, find the one that says all the fancy words correctly. Okay, so left 2. Now let's go to our calculator, clear the RAM for favor. Edgar, are you with me? Clear your RAM, go to y equals, and we didn't graph any natural log ones yesterday. They were all logs. Same exact process, just we're going to use the ln button. Okay, so ln, and then the parentheses open up for us, x plus 2. So everybody do that. Hit graph so we can get an idea of what it's going to look like in the end. Okay. Looks similar to all the other ones we did yesterday. But we're going to actually use the table to get some points. And so let's start with our asymptote. Remember yesterday we could find our asymptote by finding our first error. We're good until they get to -2. And guys, that should make sense. This is left 2. So it moves all your points. Your old asymptote on the parent function is at 0. If all your points move, so does your asymptote, so it moves to the left too. So x equals -2. That is our asymptote. So if you want to just go ahead and get that done right there. And I only see one good point. Don't bother wasting your time scrolling through this table. There aren't any that I remember, but there's really no point. I have one good point, -1, 0. The rest are all decimals. So do the best you can. Like the y-intercept is 0.69315. So where is 0.69135? That looks like it, okay? And we can just, knowing what the graph looks like, we just saw it, we can sketch a pretty good rendering of that graph, okay? Yesterday when we were graphing logs, there were several good points. Why did I have you do good points? Because we could, and it was easy. And it was a good lesson of, here's a good way to make these points. But if they don't give you good points, okay, this is not I'm not measuring this, you're not measuring this, this is good enough. Sketch. Done. There's a reason why natural log graphs come out a little funny like this. The y-axis is a little different in natural log graphs. Don't worry about it. We'll learn about logarithmic XY charts, coordinate planes in section 2.15 in January. Right now, an easy sketch of this is perfectly fine, and let's answer all the questions, okay? Domain, just like yesterday, is from like -2 to infinity, right? Nothing different. I think we're really getting the hang of domain and range, especially when we have a picture to look at. It makes it a lot easier. What's the range, guys? Yep, all the numbers. There's nothing, look at your graph. There's nothing stopping you from going down. There's nothing stopping you from going up. We use all the y values. There was something stopping us from going left. That's why the domain was affected. So the range is all real numbers. Intercepts means x-axis or y-axis intercepts. Could be either one. You might have one of each. You might have, I don't know, it could be anything depending on the graph. We know this point from our table of values was -1, 0. And we know this point too. Remember that point was 0.693. And that answer is perfectly fine if you put that right here. I'm going to show you another way that that will be written so you recognize it, even though they're both accepted. So this is fine. Here's the other way. 0 natural log 2. Where that comes from is if I plugged a 0 in for x, because x is 0, right, on the y-axis. If I put a 0 there, that's how I get natural log 2, 0 plus 2. Why am I writing it like that? It's similar to if you do something in your calculator and you get 0.3 repeating, and I say don't round it, hit math, enter, enter, and write it as a fraction because it's more exact. Same idea. This is a rounded number, okay? Which is fine. It's totally fine for this, but you might see it written like this because this is the more exact answer. If you put in your calculator natural log 2, you would get 0.693, like a billion numbers, okay? So they are the same thing. This is just more exact. Both are accepted. Concave what? Down, right? Concave down. Last part is the limit statements, the end behaviors. If you remember yesterday, they were kind of started for us. We just had to fill them in. Here we're going to write the whole thing. I was a grader this summer on the FRQ that you guys will have to take, and there's where you have to actually write your own limit statement. And it literally broke my heart. Not literally. It felt like it broke my heart because there were so many different variations of the thousands of tests I graded of what students would write. And some of them were off the wall, so they got no points. Some of them, I could tell what they meant. They knew. They were explaining to me in their own little rhythm of the way they wrote it. I knew they knew what the end behavior was, but they didn't write their limit statements correctly, so we couldn't give them any points. That will not happen to my students. All of you are going to get your points for limit statements. Let's lose points on stuff that makes sense that we might lose points if we have to lose points. Not this. So this is not me being picky. This is me wanting you to get every point, okay? So that's why I grade you really hard on your limit statements. So we always start out, so this is left, start out with LIM, limit, of the name of the function, okay? Find it. Somewhere is the name of the function. It could even just be called y. Okay, that's its name. You don't judge. Call it y. The limit of g of x, and then as x approaches, that's always going to be in every one of these. But what comes next is not always negative infinity and positive infinity. That's important. Look at your graph. We talked about this yesterday. This graph is not heading towards negative infinity to the left. It can't. It's being blocked. There's a wall up. It's not going to negative infinity. it's going to get as close as it can to that asymptote, and we have to remember to put the plus sign. That exponent means from the right. We can't get to this graph from the left. Let me give you a bad example, because I can't think of anything at the moment, of what I mean. Pretend there's no asymptote in a parabola, okay? But if I asked you how you were getting to this, you can get to this line from both directions, okay? You can get to that from the right and from the left. This one, you can only get these points. There's a wall. There's nothing over there, no man's land. There's no points over there, so you can't even talk about it, okay? So understand, if I had a graph like this, that would be approaching -2 from the left. See how all the points are on the left side? That's what's important. So if you leave off the negative or the positive, you're saying that there's points on both sides of that asymptote, but there's not, okay? Okay, anyway, so as we approach from the right, our y values are going down forever, right? Nothing's going to stop them from going down forever. All right, same for our right. Limit, name of the function as x approaches. Now let's look at our graph. To the right, that arrow, we know, means it's going to the right forever. Nothing's stopping it, right? It's just going to keep going. And as the x values increase, the y values also increase, okay? So really important that you guys, and there's an FRQ on this next test where you have to do that, so, easy points for you guys to get. All right, before we go to the homework, I have to tell you one more thing, okay? This falls in the category of important stuff you have to know for this class. You guys have gotten really, 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 really good at taking a graph, manipulating the window, okay, finding a min, a max,